Hello everyone, myself Sachin Kumar from Ajay Kumar Engineering College, Ghaziabad. Today I am going to discuss a topic. This topic is named Dijkstra algorithm, and Dijkstra algorithm is very useful if people are searching shortest path between two vertices. So if we have here a graph and we want to find out the shortest path between two vertices, then this particular algorithm may be used. And the beauty of this algorithm is it is very easy to understand, and particularly this algorithm works if we have the non-negative as is. This is the constraint with this algorithm. So if you have the non-negative, if we have the non-negative as is, then perfectly okay. If we have the negative as is, then this algorithm does not find out the shortest path between two vertices. So for the negative as is, negative bits, we have to look another algorithm, and this algorithm is called the Bellman-Ford. But for the positive bits, this algorithm is very easy to understand, and you people can find out the shortest path between two vertices. And when you have the requirement of the all pair shortest path, I mean there are graph is given, and if you want to find out the shortest path between all the pairs, then Bellman-Ford algorithm is recommended. So particularly if you want to find out the shortest path between two pairs, between a pair of the vertices, I mean between two vertices, then you can use this algorithm for the positive edges, for the positive bits. So let's start this algorithm. So as pointed out that this particular algorithm, here we have the single source shortest path problem. I mean we have here single source, and from that source we want to find out the shortest path between two vertices. For that point of view, you can use this algorithm. And second property of this algorithm is it works for directed graph as well as the undirected graph. I mean direction may be there, or direction may not be there, then this algorithm can be easily chosen for find out the shortest path between two vertices. And the third one that I have mentioned, that your edges should be positive, bits should be positive, I mean we should have the non-negative bits. So if we meet out these requirements, then we can apply this algorithm. Now, so how we can execute this algorithm? First of all, you have a graph here, and graph is basically here set of vertices and set of edges. Basically here we have a network, and this network may be road of the networks, this network may be computer networks, so it may be any network, and this network is being represented in form of the graph, and we have the positive bits for this particular network, for this particular graph. Then we can apply this algorithm, and these are here listed steps how we can apply these steps. I'm mentioning here these steps one by one. First of all, initialize the bit of every edge. As you people are familiar that graph consists of the vertices, graph consists of the edges. Then how we can define the bit of every edge? Bit means this is the distance between two vertices. For example, we have here vertex A, we have here vertex B, and from A to B, 5 kilometers is required to travel. From A to B, we can reach in 5 kilometers. So 5 is the bit, or from A to B, we can reach in 5 hours. So whatever the metric may be, time, metric may be distance, it may be any metric. So bit may be time, bit may be distance, bit may be pressure, bit may be temperature, it may be any parameter, it depends upon problem to problem. But 5 is here bit. From A to B, 5 unit is required to reach. This is the bit. So first of all, graph is given, and after forming the graph, we need to set the bit from A to B, B to C, C to D, like that. So after setting the bit, next step is pick first node. This is source, basically first node is our source, and find out the first node. This is our here source, and from that source we need to find out the distance. We need to find out the shortest distance from that source to any other destination, between pair of the vertices. This is the basic here problem. And after picking the first node, we need to calculate the distance of adjacent nodes. Any node may have the multiple adjacent nodes. So we need to find out the distance from source to its adjacents, and whatever the distance is minimum, we have to proceed it accordingly. And we need to work on the minimal distance, minimal travel distance. Say we have traveled 5, we have traveled 8, we have traveled 10, we have traveled 12. So 5 is the minimum one. So we have to apply next step on 5, not any other vertices, because distance traveled should be minimum. After that, next step is applied. For example, in this particular graph, A to B 5, A to C is, for example, 8, A to D is 9. We have here this scenario. The minimum one is the 5. So we have to work on B, not C and D, because so far distance, minimum distance traveled is 5. So we have to use this step so that we can find out the destination, and total distance traveled will be minimum in this way. This is the procedure of this particular algorithm. Now, say this particular graph is given, and see here we have various vertices here, A, B, C, D, E, F, G, etc. And we have mentioned the distance. From A to B, distance is 2, from A to D, distance is 1, from D to C, distance is 2, from C to F, distance is 5. So here, distance between, two vertices are given, and this is the here complete diagram. And since we are starting with A, you may start with any vertex, but suppose source is A, so therefore we are starting with vertex A. So we are starting with vertex A. So we have mentioned here 0, and rest of the parameters, rest of the distance traveled is infinity. Reason is that we are at A, and therefore from A to A, this is 0. We have mentioned here 0, but we have no idea about B, E, G, F initially. Therefore, we have mentioned the infinity. This is the procedure to apply this algorithm. So initially we have selected A, and we have marked here 0, and rest of the vertices, we have mentioned the infinity. Distance traveled so far is the infinity. Therefore, we are mentioning the infinity because we have not traveled. After traveling, we will set these parameters, but initially we have not traveled. So therefore, we are mentioning the infinity here. After that, now, so we are at A here, and the adjacent of A are here B. From A to B we can reach, from A to D we can reach. So here they are the two adjacents of A, they are two adjacent of A which are B and D, and distance traveled from A to B is 2, as bit is 2, and from A to D this is here 1, distance traveled is 1. So therefore, we have mentioned here 1 and 2, and rest of the values are the infinity. So in this way, we are marking the total distance traveled. So we people are able to mention the total distance traveled. So in this case, total distance traveled to reach D is 1, and to reach B is 2, minimum distance traveled is 1. So we need to explore vertex D. Our concept is whatever the distance which is minimum, we will consider this vertex for the next step. I mean, we need to find out the adjacent of D, not B, because up to B distance traveled is 2, up to D distance traveled is 1, minimum 1 is 1. So therefore, we will identify adjacents of D, not B at this moment. See here. Yeah, so we are at here D, and we have selected the D because I have mentioned that up to D, traveled is only 1. Up to V, traveled is 2. Therefore, we are considering D. And from D, if we are at the D, then adjacents of D to G, we can reach from D to G, we can reach from D to E, and D to F, D to C also. So there are here these possibilities. If we are at the D, then adjacents of D are E, G, F and C. So see here in the next step, if we are at D, it was 1, and from D to E distance traveled is distance traveled is 2, 1 plus 2, 3. In same way, D to G, up to D distance traveled was 1, 1 plus 4, 5. And in the same way, up to D it was 1, 1 plus 8, 9, and 1 plus 2, 3, 1 plus 2, 3. So we have mentioned all the distances, and vertex A has been explored, vertex D has been explored. Now we need to find out the minimum one from rest of the vertices. A has been explored, D has been explored, and rest of the vertices are B, E, G, F and C. So minimum one is 2, because this is 2, this is 3, 5, 9, 3. So minimum one is 2. So we need to work on the B because this value is the minimum. Now vertex V will be explored. Yeah, we are exploring here vertex B. We have taken here vertex B here, and adjacent of B are D, E, So 2 plus 3, it will be 5, but already minimum one is 1. So therefore we are not taking 5. We need to take the minimum from A to D. Direct one is 1. Via V, so 2 plus 3, it will be 5. So therefore we are not taking 5. And B to E, 2 plus 10, 13, and already this value is 3. So therefore we will not overwrite it. We will take previous value. This is the 3. So we are considering here 3. So already vertex B has been explored. Now rest of the vertices are E, G, F and C. E and C, these two vertices have the minimum value, which is 3, and rest of the vertices G, F and G have the 9 and 5 values. So minimum one is given to C and E. So C is 3, E is 3. So there is a tie. So you can choose either C or you can choose either E as the next vertex. The choice is yours. Choice is yours. Yeah. So we have taken here E. We may take the C. There is no doubt in it. But this is the choice of you. So we are taking here E. So if we are taking here E, then adjacent of ER from E to G we can reach. So 3 plus 6, 9, and already value is 5. So we cannot override it. Vertex E has been explored. Now rest of the vertices are C, F and G. C, F and G. So C is 3, F is 9, G is 5. So minimum one is C. So we need to take C as the next vertex. Yeah. So C is here 3. Adjacent of C is F. So 3 plus 5, 8, and we are taking here 8, 1. Now we have here two choices, 5 and 8. So minimum one is here 5. So we need to take G. So we are taking here G, and this one is 5. 5 to 1 plus 6. Previous value was the higher. So it will be overwrite it. 5 plus 1, 6. So we people are able to take 6 here. Now, so we can find out the distance from A to B. This is 2. A to D, this is 1. A to G is 5. A to F is 6. A to C is 3. A to E is 3. So in this way, we have here source is here A, and from the source we can find out the distance from A to B. We can find out the distance from A to D, A to E, A to G, A to C, A to F, like that. So in this way, we can find out the shortest distance between a source and other vertex. We can find out the shortest distance between a source and another vertex from rest of the graph. So in this way, we people are able to find out the shortest distance. And shortest distance, has a lot of applications. You can apply this concept in real life, how we can find out the shortest distance between two cities, so that you can travel the optimized route. Similarly, in computer networks, we have a lot of traffic, and how packets are transmitted from source to destination. Computer networks are also use the routing algorithms. So you can use this particular algorithm as another routing algorithm. So this algorithm has a lot of applications, and you can find out the shortest path between a source and another vertex from rest of the graph. So it is all about the Dijkstra algorithm. Thanking you. Thank you.